Greetings, chemistry students. Today, I'm going to teach you how to do stoichiometry. And stoichiometry comes from the Greek word stoichion, which means element, and metry, meaning to measure. So stoichiometry literally means measuring elements, but the modern meaning of stoichiometry is essentially determining quantitative relationships in a chemical reaction. And you may remember Moletown, where we have moles, and I'm going to draw this in a slightly different arrangement. We have grams and we have particles. And the relationship between moles and grams is the molar mass. That's the numbers off the periodic table. And the relationship between moles and particles is right on the front page of our reference tables. 6.022 times 10 to the 23rd particles is a mole. Now this all works out well if we're just talking about a single substance, compound A, for instance. We can do this exact same thing for another substance, substance B. Now, what stoichiometry allows us to do is to connect these two things. We can go from moles of substance A to moles of substance B. And to do that, we use the coefficients in a balanced equation. So for instance, if we take a look at this chemical equation right here, if we balance it real quick, we put a 2 right there and a 3 right there. What this tells us is for every 1 mole of nitrogen, we need 3 moles of oxygen, and we will make 2 moles of NO3. Or if you had 2 moles of nitrogen, you would need twice as much, or 6 moles of oxygen, and you would make 4 moles of NO3. Or if you had half a mole of nitrogen, you would need 1.5 moles of oxygen, and you'd make 1 mole of NO3. In other words, these react in a 1 to 3 to 2 ratio. That's called the stoichiometric relationship. So we're using coefficients as mole ratios. And I'm going to show you how to do a couple of stoichiometry problems here. So let's look at this first problem. It says, how many moles of NO3 are produced if 5 moles of oxygen react? So we start with what we're given, which is 5 moles of oxygen. And then we're trying to find moles of NO3. So we're going from moles of oxygen to moles of NO3. So we just need to set up a conversion factor where we're going to go from moles of oxygen to moles of NO3. And the numbers we're going to use here, I know every other time we've gone from grams to moles or moles to particles, we've always just used 1. But in this case, we're going to actually use the coefficients from the equation. So oxygen has a 3 in front, so we put a 3. NO3 has a 2 in front, so we put a 2. And then we solve this, and it's 5 times 2 divided by 3. And then we just get our calculator. And in our calculator, we do 5 times 2 divided by 3 equals 3.33 moles of NO3. In the second problem, it says how many molecules of NO3 can be made from 7 moles of nitrogen. So we're starting with 7 moles of nitrogen. And we're trying to find molecules or particles of something else. So this problem is going to be 2 steps. Our first step is to switch from moles of what we started with to moles of what we're trying to find. So we're going to go from moles of nitrogen to moles of NO3. Because we started with nitrogen, we're trying to get to NO3. When we set these up, whatever's on the top needs to appear in the bottom in the next equation so that those units will cancel each other out. Now the numbers we use here are our coefficients. Nitrogen doesn't have anything in front, so we just assume that there's a 1 there. NO3 is a 2. That gets us to moles, but we're trying to get to particles. So our second step is we're going to go from moles of NO3 to molecules of NO3. And here's where you need to be really careful. In this relationship here, in these relationships, we don't use the coefficients. We just use the relationship that 1 mole is 6.022 times 10 to the 23rd molecules. I know it's very tempting to use a 2 again, but we don't. We only use the coefficients in this new step. So then we take our calculator, 7 times 2 divided by 1 times 6.022 times 10 to the 23rd divided by 1 equals 8.43 times 10 to the 24th. Molecules. All right, so number 3. We're trying to figure out how many grams of oxygen are needed to produce 75 grams of NO3. So we're starting with grams of NO3, and we're trying to find grams of oxygen. So we're going to have to go from grams to moles, moles to moles, and moles to grams. This is as many steps as you can have in a stoichiometry problem, which is 3 steps. So we are starting with 75 grams of NO3. So our first step is to go from grams of NO3 to moles of NO3, where 1 mole equals the mass of nitrogen plus the mass of oxygen times 3. And so that is 62.01 grams. The next step is to switch compounds. So we started with NO3. We're trying to find oxygen. And the relationship is that 3 goes with oxygen, 2 goes with NO3. This is the only step where we look at the chemical equation. Then in our third step, it's wanting us to get to grams. So we're going to take our moles of oxygen and go to grams of oxygen. And the relationship here is that 1 mole of oxygen equals the mass of oxygen times 2. And 16 times 2 is 32. So then we just take all of this and we put it in our calculator. So take 75 times 1 divided by 62.01 times 3 divided by 2 times 32 divided by 1 equals, and that comes out to be 58.06 grams of oxygen. Now, we're going to look at a different reaction. So here I've got another type of reaction. This is, as you might can tell, a combustion reaction. I've already done the favor of balancing it for you. And in this problem, it's asking us if 3.8 times 10 to the 24th molecules of oxygen react, how many moles of water are made? So we're starting with 3.8 times 10 to the 24th molecules of O2. So we're starting with particles of something, and we're trying to get to moles of something else. This is just 2 steps. In our first step, we'll go from particles to moles, or molecules to moles. The relationship is 1 mole is 6.022 times 10 to the 23rd. And then in our second step, this is where we cross the bridge from moles of one thing to moles of the other. So we're going to go from moles of oxygen to the thing we're trying to find, moles of water. There's an 8 in front of the oxygen. There's a 6 in front of the water. And so we will take our trusty calculator, 3.8 times 10 to the 24th times 1 over 6.022 times 10 to the 23rd times 6 over 8. And that equals 4.73 moles of water. And this last one, I'm asking us how many grams of carbon dioxide are produced from the combustion of 100 grams of C5H12. So we're starting with 100 grams of C5H12, also known as pentane, and we're trying to figure out how many grams of carbon dioxide are made when that happens. And this is the problem for you to do. And I want you to submit your answer in Google Classroom.